Hello everyone, good morning and welcome again to one of our online science class. How was your week so far? Is it great? That's awesome. Well, today is April 21, it's Tuesday, and we're gonna have another exciting topic for science. So kindly prepare with you your course book, your extra paper for solving and for note taking because we're gonna have an exciting topic for today. So if you don't have them, kindly hit the pause button right now. Get all those materials and be ready. However, if you all have them right now, let's guess this sound that I'm gonna give it to you. Alright, so you need to put your volume up and listen carefully. Use your ears well. Alright, so here's your question number 1. Listen carefully. So you're gonna name here that thing that produces this very familiar sound. So what do you think is this? Time is up. Let's see if you get it correctly. And of course, this is definitely an ambulance. Did you get it correctly? That is awesome. Here's your question number 2. So what do you think is that sound? Kind of familiar, right? But it's not your cell phone, it's the fire alarm. Well, I bet that you never heard one because your house is safe from fire. Well, let's proceed to question number 3. It's a little bit distracting to the ears, but what do you think is that? Familiar? And of course, that is a television set with no signal. Did you get it all correctly? Kindly let me know of your mark on the comment section below. I'm gonna record it if I see it. So, what do you think is our topic for today? We're talking here about some sounds over here. Oh, speaking of the sound, that is the sound. So, what do you think is our topic for today? So our topic for today is all about definitely sounds, but we're going to talk here about how sound travels. And we're going to take here into account the sound waves and how does it travels and how do we hear them. So if you have your course book right now, kindly open it on pages 140 and 141. We're going to learn here what media does needed for your sound to travel, and we're going to investigate how does the sound travels in those media. By the way, we're going to define here later what is the meaning of the word media, and also we're going to connect this topic with our previous topic, and that was last Sunday about calculation of the frequency of the sound. Are you ready? Well, I'm ready, and let's go. So first is, well, a while ago I gave you the sound of a well, that was a different siren, and I have here a police siren, but the picture there is a fire truck. So, well, anyway, how can we locate the fire truck or the police siren even though we didn't see it? But we can locate that it is very near us or it's farther away from us, and we didn't see it. So, because the sound waves travel through a media. So, you might be asking, what is a media? A media is any material that allows sound to travel, and we're going to expound here how do sound really travels in a media and why sound needs a media for us to hear it and for it to travel. Well, we're gonna answer that question by this experiment. So I'm gonna give you here, if you attended the Zoom live session, we did it with a drum and with a styrofoam. However, on this recorded video, I just put this video right over here. So I have here a loudspeaker instead of a drum. It's easier that way and it's louder that way. So I also have here the rice. I put the rice on the plastic set over here. So this is a thin membrane. Well, on our Zoom live, it is a plastic and I put it here. So please observe what will happen and kindly answer the question at the top. Be prepared for that. I'm going to ask you later. Why do the rice move when we turn on the loudspeaker over here? Alright, so please watch this one. We're going to add a lot of rice so that you can really see how does it look like. We're gonna put it on the middle. We'll arrange it that way. And this time we're gonna turn on the speaker. So listen. Well, that is a loud sound actually. Try to see what happens to the rice at the top of the thin membrane or the plastic. What's happening? So definitely what's happening here is the rice also vibrates together with the sound in front of the speaker. So there is something that makes this rice move, and what is that? Definitely it is the vibration. So where is this vibration coming from? It comes from the speaker because it has sound, and sound can only be produced because of the vibration. So let's take a closer look at that experiment. If you notice, the loudspeaker is not touching the rice here, and it's not even touching the apparatus that we have here. It's a glassware, and we put a plastic over here, and we use the same thing in our Zoom live session that just a while ago or just this morning. So the question here is, the loudspeaker is not touching the rice or the plastic setup, so how can it make the rice move? That is the question. So what do you think? If you think something else, please write your answer on the comment section below. I'm really interested in what's going on in your mind. So let's take a closer look with this. So on this experiment, we will be needing a glass jar or a bell jar. That's right over here. And we need this sound source here. So what we're going to do is, we're going to put the sound source inside a bell jar, and we need these two tubes. These two tubes will suck out all the air from the bell jar. We call this one as your air pump. So let's take a look now what will happen next. So if you notice, we can still hear the buzzer, right? We can still hear the sound. It's very faint. But try to see what will happen as we remove the air. Okay, I'm gonna repeat it one more time, and I really need you to listen carefully, to be observant with what's happening, the sound of the buzzer over here. Alright? So let's replay it a little bit. So what have you observed now? We remove all the air from the bell jar. Can you still hear the buzzer? Yes or no? Well, definitely no. I can't even hear it. Well, in our experiment this morning, we did it also with a bell jar, and we pumped all the air also, and the same thing had happened. So this is the stage 2 of the experiment. So what we did here is we removed the valve so that we can release, we can return the air back inside and try to see what will happen. So simply what happened is the sound went back. So we can hear it back again. Alright? So here is my question. why we cannot hear the sound when we remove the air from the glass jar. What's the reason? If you know the reason, kindly put it in the comment section below. Well, that will count as your participation. So the reason is there is no air inside the vacuum. So we call this now the bell jar as your vacuum because we remove all the air. Vacuum is an ideal space or an ideal apparatus which removes all the air so that no medium, again a medium is anything that allows something to pass through or to travel, in that case the air. So when we remove it, and that's the reason why we cannot hear the sound. So no air is found in the vacuum where the sound would travel. So this is my question. What does the sound do to the air that makes us hear it? So in that case, we are asking here about the media, and that is the air. What does it do, or what happens to the air? That's why we can hear it. And how does it travel if it allows the sound to travel through it, and that's why we can hear it. So try to look at this one. So in this experiment, I have here a speaker, a very big speaker, because we need to have a loud sound. And again, to amplify the sound, that means that to make the sound higher, to make the sound really on a volume up. If you attended our Zoom live session this morning, what we did here is we used a drum and we used a candle so that I can show to you what happens here. So I want you to observe and to answer the question here. Of course, you are expecting here that the flame would move. Well, some of them might be turned off. But this is my question later. It's neither touching or really near to the flame, but it's a little bit far apart. So the question here is why it's capable, I'm talking here about a loudspeaker with a sound, with a very loud sound, is capable of moving the flame. So let's watch this one. Well, there's gonna be sound in a little while, so just take a look with that. So we have there the speaker, and we have a lot of candles. So it's a very big speaker. And try to see later what will happen to the cover of the speaker, and we'll tell you what's happening if a sound is produced. Try to look at this. So if there's a sound, it's bouncing back and forth. So try to remember again what is the meaning of the word vibration and how is it related to the sound. So this time we're going to turn on the candles just like that. And we are playing the sound right now, and I want you to turn on your volume really high to listen to it. Well, some candles turned off. So if you notice the flame when it was zoomed, so what happens there is that it keeps it moving also on the direction of the sound wave. So it's towards outside one line from the source of the sound. So if your loudspeaker or your speaker is moving just like this one, so it follows also the movement made by the flame. So why does the flame moves at this time? So it describes here the movement of the sound using this longitudinal wave. So what I have here is the red. The red is the moving back and forth. By the way, I slowed it down so that you will see it really clearly. So this one now is our source of sound, and that is the bass or the speaker of the very big speaker right over here. And the black things that you can see here are the air particles. So notice that whenever we vibrate the speaker, we push the air particles, and some of them are pulled back, and this is the reason why the air vibrates. So again, the speaker vibrates, thus vibrating also the air molecules just present around it. So this one, it's pushing it here and pulling it here, pushing it, Well, it happens in a very fast pace. It's like what you can see a while ago there with the flame. It's moving back and forth very faster. But here in the on the video that I'm showing you here, another one is longitudinal wave. It's slower so that you can see that. So this wave here would represent one complete vibration. So this one is one complete this one is one wavelength to the other wavelength, and this one now is your one complete vibration. So it's called longitudinal wave because this sound tends to travel in waves, and it's only in a straight path. Hence, it's called longitudinal wave. And this is the pattern or the path at which your sound wave travels. So molecules are being pushed on the next ones. Molecules here vibrate side by side outwards through the air. Hence, it's called longitudinal wave. So again, the sound source is from the speaker and it travels through the air. And this is the reason why the air becomes the medium for the sound to travel. So the sound source is in here, and because of the candle experiment, it tells you that the air around the candle or the space between the candle and the source vibrates, and that's the reason why when it reaches our ear, it allows a part of our ear, and that's what we're going to discuss on our topic about ears. Maybe that will be next week, and that's the reason why we can hear it. And again, that is all because of the vibration. I really want you to take note of the very important concept right over here at my side of what's happening to the air molecules, and this is the reason why we can hear it, or this is the reason why sound tends to travel through this medium on the air. But this is my question: can sound also travel in solid or liquid? What do you think? Or does it only travels through air? Well, I'm gonna give that to you to answer. I'm gonna leave that to you to answer, and that will be part of your assignment, so you can do some little research about that one. So this is a close-up view of the air. This is, on the other hand, the string of a violin or a guitar. I'm gonna play it back again, and the white things around you is the air molecules. This is a special camera which can capture sneezing. They can capture different kinds of particle that is moving, and it's being done by using a very powerful camera that can capture slow motion. And I want you to take a look what happens here to the air particles as I move the string. So this is one wavelength, and this is one complete vibration. So try to observe what happens to the air particles. So just try to imagine this air particles here, well, the mass of it tends to go to your ears. So what would you notice? Of course, you are going to hear the sound from the source. So the larger or the higher is the volume, the larger is that mass or that vibration that you're going to take, and hence we will have a higher amplitude on the sound. So I want you to recall what is amplitude, and thus the sound becomes louder. But of course, if I make that vibration lower, what will happen is I'm also going to hear a very soft sound. So the air molecules here tend to travel in the direction of the sound waves, hence we called it a while ago as your longitudinal waves, and the air molecules are being pushed side by side by the waves, and that is the behavior of your sound waves, and thus your air now is a medium for your sound to travel. So this is my question. We're talking here about sound waves and how it behaves. So by the way, before we answer that question, I want to show you this to you in this video. We call this acoustic longitudinal wave. The acoustic there stands for sound, and longitudinal wave, that's what we discussed a while ago. That's the direction of the sound wave. And this is the speaker, and I am just interpreting it on a sound wave here. And we usually use a certain kind of apparatus to show this kind of wave. So if you notice, well, this is another kind of sound wave. This is another kind of sound, not related to the sound that I let you hear a while ago. So if you notice, there's a pushing and pulling, or which we call that the vibration of the air that occurs here, which is interpreted here now by the apparatus, thus showing the wavelength here as a wave in a line, in a line representation, just like this one. Okay, so it's in a wavelength. So if you notice, the height of the wavelength here, is it high or low? So the clue here is look at the amplitude. Again, the amplitude here is the height of the wavelength that you can see here, or the height of the wave here. So the sine wave here is a vibration of the molecules, and if you look at the amplitude here, what have you noticed? Is it high or is it low? So if I have a high amplitude here, is it loud or soft? Well, I'm gonna leave that to you to answer, and look at the waves. Are the waves here shorter or are they closer to each other? Try to look at the space. So if you look at the space here, is this sound a low pitch or a high pitch based on its frequency? So take a look with its spaces. Well, what is your answer? If you answer low pitch, you were correct. But why it's low pitch? Because the frequency here of the wavelength is far away from each other. There's a lot of space, so it's definitely low pitch. So when will this become a high pitch? Exactly. If the spaces between the wavelength are shorter and are closer with each other, well, that is a high pitch. Well, we're talking here about low pitch and high pitch, and that talks about the frequency of a sound. So let's practice now. We discussed this one last Sunday. Let's practice now solving for the frequency of the sound. So I have here this situation at the top. If a bird flaps its wings up and down, which of course creates sound, the bird does it for 50 times in just 20 seconds. Well, that is pretty fast. What is the frequency of the flapping? So we're gonna solve here the frequency. So first, of course, when we are solving any problem, we need to identify the given on the problem. So given there is the time, and that is the 20 seconds. Of course, you will know that's the time because there's the unit seconds on it, and the vibration says here that it flaps its wings for 50 times. So we're gonna use the formula for finding the frequency. Can you still recall it? What is it? Exactly. The formula to get the frequency is F, shortcut or abbreviation for the word frequency. It's vibration over time. So what we're gonna do right now is to replace the variables here, the vibration and time, with the numerical value on our problem. So vibration is 50 times divided by 20 seconds, and that will give us a value of F is equal to 2.5 Hertz. So simply divide 50 by 20 and you will get 2.5 Hertz. Therefore, the frequency of the flapping of the wings of the bird is 2.5 Hertz. So what does the word Hertz mean? It's a unit for frequency. That is right. So 1 Hertz is equal to 1 vibration per second. So if you say 2.5 Hertz, it means that you have 2.5 vibration every second. So was it fast enough or not? Well, it's pretty fast enough, and it has a low frequency compared to other types of frequency. So 2.5 Hertz is not that high pitch at all. So let's consider it as a low pitch. Alright? So let's take a look with question number 2 over here. A string has a frequency of 60 Hertz at a period of 50 seconds. This is another different scenario. How many times did it vibrate? So what we're asking here is the number of times the string has vibrate. So how can we solve for that? Of course, first we need to write the given. So the given here are the time and the frequency So if you take a look with the previous problem that we have, even here is the time and vibration we need to find for the frequency. But here, given are the time and frequency, we need to identify the number of vibration which has been made to produce the 60 hertz of sound. So given here is 60 hertz, and that is your frequency. How about 50 seconds? Exactly. It is the time. So the formula to get that, I want you to take note of that. If you have your notes with you and your pen with you, prepare that and kindly take note of this so that you will not forget it. So V, which stands for the vibration, is equal to frequency times time. And of course, you need to replace the variable here with the numerical value. We have the frequency, which is 60 hertz, and the time, which is 50 seconds. So just 60 multiplied by 50, and that will give us a value of what? Exactly. Excellent job. We have 3,000 vibrations. So the unit that we're going to use here for the vibration is just simply vibrations. So, or 300 times. So the string has to vibrate 3,000 times in just 50 seconds to create a 60 hertz frequency. Is it a high frequency or low frequency, by the way? Well, based on the number of times it vibrates, it's really high. So definitely the string has a very high frequency. So it's a high pitch frequency. Great. So let's take a look with the third question over here. So the drum skin has a frequency of 75 hertz, which vibrates for 500 times or 500 vibrations. Well, this time it's another totally different story. Calculate the time when the drum skin produces this frequency. So here, what we're asking. Awesome. We're asking here for the time. So let's write the given. Given here are the vibration and the frequency. So what is the value for vibration? Excellent. That is, this one, is it vibration or frequency? Nice job. It's the frequency. And how the vibration? Of course, you have the clue here, which is the vibration. So 500 vibration. And what is the formula? Again, take note of the formula. So time is equal to vibration over frequency. So take note of that formula. And we're just going to substitute these variables here, vibration and frequency, with the numerical value on our problems. And since we write it in the given, vibration is definitely right. 500 vibration, and our frequency here is excellent. It's 75 hertz. So just divide 500 by 75. And of course, our value here now will be seconds. Since hertz is in seconds, it's the number of vibration for every second. So what value of time do we have? Did you solve it? What's the answer? Excellent job. The answer to that is time is equal to 6.7 seconds. So 75 hertz, do you think it's a high frequency or a low frequency? A high pitch or a low pitch? While guessing on the number of vibrations for every second for 6.7 seconds, it's pretty high frequency. It's a very high pitch. So did you get it correctly? That's awesome job. So did you get all of these examples? So I just want you to take note of the formula right over here. So we use this three formula. If you have your pen and notes with you, you can hit the pause button and take note of this. Frequency is equal to vibration over time. Time is just equal to vibration over frequency. And vibration is equal to frequency times time. If you need more time to revise with this video, kindly hit the pause button and move the cursor backwards, rewind that, and try to review it one more time. If you're ready, let's test how much you've learned so far. We're gonna have here some solving, so prepare with you your pen and paper. Are you ready? Well, I guess so that you are ready. Let's have your mind tested. Alright? So here's item number 1. You have a minute to solve for this. Your time starts now. Time is up. What's your answer? A string here of a guitar vibrates 70 times in just 3 seconds. We're gonna calculate here the frequency of the string. So, given here are 3 seconds and the vibration 70 times, use the formula vibration over time. That will give us a value of frequency, which is 23.3 Hertz. So 1 mark for the given, 1 mark for the formula, 1 mark for the working, and 1 mark for the final answer. Did you get it all 4? That's awesome. Let's proceed to item number 2. I'm gonna give you a minute again to solve for this. Your time starts now. Time is up. The vocal cords has a frequency of 55 Hertz. Well, probably this baby at the top. And to produce the sound, it needs to vibrate for 90 times. How long does it take to produce this sound? So we're talking here about time, right? So what is your answer? Can you hear it? Let's check if you got it correctly. So frequency is equal to 55 Hertz. Vibration is 90 times, so use the formula over there. It's vibration over frequency to get the time. So let's replace the variable vibration with 90 times or 90 vibrations in frequency, which is 55 Hertz. So all we need to do is divide 90 by 55, and of course the value for time should always be in a unit of seconds, and the answer is 1.64 seconds. Did you get it correctly? Well, if you get it correctly, that is great. And let's proceed now to question number 3. Question number 3 here, the wings of the bee has a frequency of 30 Hertz for 0.5 seconds. How many times did it vibrate? You have a minute to solve for it. Time is up. Let's see if you get it correctly. What is your answer? Are you sure of that? Well, let's take a look and compare it with the answer that I have here. So frequency is equal to 30 Hertz and our time here is 0.5 seconds. So what formula are we gonna use? Its vibration is equal to F, or the frequency multiplied by time, and substitute the variables here with the numerical value we have from the problem. That's 30 Hertz multiplied by 0.5 seconds, and that will give us a value of 15 vibrations. Did you get it correctly? How many marks did you get? Did you get all 3 correctly? Well, that is a total of 12 marks. Please write your mark on the comment section below or send a message to me. I'm really interested in how much you get. You can revise this video one more time, just return or just rewind. You can watch it on your most convenient time and you can repeat it over and over again. Or you can send me a message if you want any clarification or you have any questions. So here is my question. This will be my very last question after those mind-boggling quiz. You have a minute to do this one. How do sound travels? Please let me know of your answer on the comment section below. The best answers will be featured on our Google Classroom. Well, I have here an example of how I did it. Sound waves travels through a media, and sound travels when the particles push each other's back and forth. And I want you to make your own definition of the word sound. How does sound travels? So please let me know in the comment section below. And if you get it nicely and if you get it very scientifically, I might post your answer on our Google Classroom. Well, what are you waiting now? Type it now on the comment section below. So if you have questions or clarifications, kindly send me a message on our Google Classroom or on my email, or type in the comment section below. So that will be all. Worksheet will be posted on Wednesday. See you next week. and we're gonna have another exciting topic. Goodbye, everyone. See you.